Thank you, Ross. Thanks, everyone, for inviting me to talk today. So I'd first like to, acknowledge my colleagues, our CTO, Doug Shooten, and the geoscience team at Ideon, Reed, Alex, Goodney, Shreen, and Stephen, whose work I'm going to be presenting today. I'll talk a bit about kind of our physics and the methodology, our primer that we usually give on the Muon method. And then I'll go into case studies of different lengths, focusing on different applications. So there'll be resource characterization, geotechnical applications, and exploration, and block caving as well. And we'll see how it goes. Feel free to jump in and ask questions as we go. So the methodology, we use the energy from supernova explosions, and the energy has traveled for billions of years and billions of light years. And when it interacts with the upper atmosphere, it causes a chain reaction, and we get all kinds of exotic particles like kaons and pions and things like that. And when those particles, a lot of them decay very fast, but when they shower down and hit the surface of the Earth and start to go underground, 99% of them are muons. And we use the muons, which is a kind of like a heavy electron. And we use the fact that it's traveling very fast in a straight line and is of high energy because it can penetrate down to 1 to 2 kilometers below the Earth. And there's a constant flux of muons going on. They come and go in all directions, and it's somewhat constant. It does very slightly, but there's about 1 per minute for every square centimeter at the surface of the Earth, and that equates to about 1 per second through the top of your head. And they're of high energy, but they do lose energy as they progressively pass through matter, pass through the Earth. And as they as they encounter high density material, they do lose energy at an accelerated rate. So that allows us to basically count muons. And if we count the muons that survive to depth, and we know that there's a kind of a paucity of muons in one direction versus an abundance of muons in another direction, we can then infer something about the density coming in, basically a directional density that we get, and that allows us to know something about the geology. So this is what it might look like for an exploration situation here, where we're imaging an ore deposit. We've got a straight path of the muon here, and we've got high density material that could be massive sulfide that would generate a shadow essentially on our detector, on our imaging platform here. And we would have a shadow where there's high density material above, or we would have more muons counted where there would be low density if there was a void or something like that. And we've got an upward looking aperture of about 120 degrees. And we can put these detectors down to about, we've gone down to 1 kilometer. We've done our modeling down to about 1.5 kilometers. And it's really a function of the target that you're trying to image and the time that you can image for, and the number of detectors you can put down. So just like X-rays and CT scans that allow us to see inside the human body, we can image the Earth. Now, there's a lot of analogies with geophysics and medical imaging. I did see yesterday somebody was talking about X-raying the Earth using potential fields, and it's like, well, it's not quite an X-ray, but it's still great technology. But this is actually not an analogy. This is an actually using the same physics. So we have a radiation source. We have particles that get attenuated as they go through different densities of material. And then we have a way of collecting that information on a radiograph, just like an X-ray. So it allows us to see inside the Earth. And the fact that they're traveling in straight lines gives us really good resolution. So we have an achievable density resolution of about 0.1 to 0.2 grams per cc, and an angular resolution of about 1 to 1.5 degrees. So that gives us about 1 to 2 meters for every 100 meters away from the detector. That's when we get enough muons. Obviously, if we get fewer muons, we won't be able to resolve as well. So it is a matter of a function of survey parameters as well, where the detectors are located and the depth and the duration of which you're requiring muons. So I'll get into our first case study here. I'm going to talk about Olympic Dam and some resource characterization and void mapping. The idea is to try and kind of map the mine, map the ore body, essentially, and to try and reduce cost in understanding the ore body, while reduce the amount of drilling as you can try and mine an ore body. And so there were two main objectives. One is to map backfilled stopes, so geotechnical features, and then also map mineralization, the extent of mineralization, with another objective, which is always there, which is, can you find any new ore bodies? And Olympic Dam it's massive. It's a huge deposit, and so we started to along this concept of trying to map the whole deposit. But we started in one area called the greens that I've got kind of here. This is the map of the. Let me see that. Yeah, the map of the deposit, and we were just kind of mapping a small part of the deposit. We started with 3 detectors down to about 850 meters, and then we went. Subsequently, we went to 15 detectors after some support and input from BHP, and then we got 15 detectors deployed down to 920 meters. And this is showing kind of our upward-looking view of the Earth from this. And the first deployment with the 3 detectors, we were able to demonstrate that we could see the backfilled stopes and we could map the mineralization. So we just took it to that next level, trying to get more resolution and information. This is a picture of the detectors and how they're deployed in mine. So they're up out of the way. You can wirelessly connect to them in the mine, and then we can transmit that information through satellite back to our offices in Richmond. And they're for purpose. They're ruggedized, and they're for emplacement in mine. And you just power them up, and they will collect muons. So this is the survey configuration that we used. We have the detectors. Well, first of all, we have the mine stopes here in gray and the mineralization targets in red here. We are all underneath an overburden stratigraphy, so we're just concerned with what's below the stratigraphy. And we place the detectors in the mine workings in the center here. And then as I move around, we'll see these fields of views that would come from each of the detectors. And so it's where we get those intersecting fields of views allows us to do the 3D inversion. And that's kind of the view that we have in the mine. So the target is to image directly above, but also try to see off the side as well of where the detectors are placed. And this is another view just showing them in the mine workings. And we put them in place in last May, and we've wrapped up this. We're wrapping up this survey now, but the results I'll show were from about the three and a half month time period. So we had data up to 3.5 months, and we produced intermediate models, and that's what I'll show you today. And this is a picture of the data that we get from the detectors. So this is our Z-score, and it is a measure of deviation from an expected muon count. And so this is a normalized data, and it's normalized by the expected count given a half space or given a constant density. And we know quite well our uncertainty. So this is given in standard deviations. So we've got up to +4 or -4 standard deviations here, and anything above 2 standard deviations or below -2 standard deviations would give us 95% confidence that that signal is real, and we've got confidence in that. Yeah, please.
How do you get the estimated background space count? Is that something that sort of how many muons?
So that's through a forward modeling engine, and we've got a model of the muon flux at the surface that we can propagate through and get that. So that's really the trick, is understanding what that model of flux is. Yeah. And that flux does vary slightly with seasons, but in general, it's quite well understood and quite well known.
Okay.
Yeah, it's been researched for close to 100 years now. Yeah.
Oh, that's fun then. So the cone, 120 degrees.
Yeah.
Is that the limitation of the sensor, or is it just penetration energy?
That's a nominal cone. I mean, if you have shallower detectors, it's really a function of the path length through the Earth. So the deeper you are, maybe it will be a little narrower. Shallow detectors, you can go wider.
So even if you were to rotate your sensor, that cone is really like physics.
Yeah, the sensitivity might change slightly just because of the physics of the detector, but essentially, yeah, it comes from above. Yeah. Yeah. So on the left column here, these are the top row is from a depth of 870 meters, and this is one detector position. And on the left, we have what we expected from the block model that the mine provided, and on the right is what we have imaged in the field. So you can see the areas that are red would be more muons, so that means low density features, and in the blue will be high density features. And this is a rectilinear projection. In the center will be straight up, and we've got basically an angle off the vertical, off the zenith, in the X and Y here. And so we've got low density features that we're seeing in red here, so backfilled stopes, and then on another detector location here, we can see the mineralization. There is a good relationship. This is an IOCG deposit. There's a very good relationship between density and grade. So that's why we can say, okay, yes, it's useful for mapping grade. I'll just move on. So this is after 4 months, so halfway through the deployment. This is a section through one of our inversions. So this is we're constraining the overburden, and it's unconstrained below the overburden. It made quite a difference, and so the overburden is quite well known, and it made sense to put that in there. And then all the mineralization is below that unconformity there. So on the left, we have our inversion model. On the right, this is the block model. And we've also got a few shapes showing the stopes here and here. In general, there's a good correlation with our low density stopes here, and also the mineralization. One feature that kept popping up for us was, I'll just show this here. So these stopes are mostly backfilled. There was a stope in this area that kept showing up in our data. It wasn't mapped as a stope, and it was the lowest density feature that kept coming up in our model. Turned out it was half filled with air, half backfilled. And so we could actually see that internal structure of the stope. And so that was the level of fill of that stope. So we were able to kind of map that stope internally as well. And the high density features to the left here are also kind of quite consistent with the high density features here. And to the side here, we've got slightly less resolution because we are kind of coming away from where the detectors are, but we've mapped the edges of the mineralization here and here, but we're not able to map the stopes out to the side here, which isn't a surprise, and that's kind of expected here. So we've got, mapping the stopes and then mapping the mineralization. This is an image showing a cutoff of, I think it's 3.1 grams per cc in the orange shell here. The stopes are in blue, and then the mineralization from the mine, from all the drilling, is in green. So I will show a little animation of this, but in general, the stopes are located where the low density features is, or where the high density features are not. And then the mineralization correlates quite well with our high density envelope as well. And I'll just move that around so you can see the stopes in here. And then also in this embayment, there's the high density wraps around the stope as well. And yeah. Like all the mine workings and everything, or no, it's very little mass compared to that amount of rock that's there. Yeah. There's, in some situations, we have seen, maybe shallower examples, we've seen areas where a stockpile can make an impact. I'll actually show that on the next case study. Yeah. I will just move forward. So as well as providing a density inversion, deterministic density inversion, we're also doing some Bayesian inferences, and we're providing an uncertainty model. So this is showing our standard deviation from our Bayesian inversion throughout the models, throughout the space here. And you can see we've got a smaller standard deviation closer to the detectors in this region, and that was really the goal of the survey here, was to map this area. And then it does get a little larger as we move over to the sides here. And this standard deviation, we are calculating the full covariance matrix. So this is just the diagonal of that covariance matrix to extract this. I'll talk a little bit about what else we can do with that covariance matrix. So we've developed a closed form solution to this problem, because we've got a really good understanding of our uncertainties, because it's a stochastic process. We understand that really well. And so we're able to generate a covariance, posterior covariance matrix. And then we can interrogate that for not just the density distribution for each cell in a voxel model, but also we can look at a likelihood parameter as well. So we can interrogate it and come up with what we call confidence intervals. So we can say things like, what would be the confidence of a surface that is, or map a surface in 3D that provides greater than 95% confidence that we are above 3 grams per cc, or something like that. So it's a quantification of uncertainty given the confidence and the density kind of coupled together. And that's just, one of the things we can get out of that Bayesian inference. And this, we're applying it to voxel inversions, but also geometric conversions and geometry inversions as well. And then we had some validation around this. We did, parts of the mine have been drilled to different extents. So they're inferred, they've got their indicated, they've got their measured parts of the mine. And we wanted to compare it over an area which is well drilled out. So this is in the measured part of this part of the deposit. We did a comparison between what we have versus what the block model is providing. And we were able to recover a density accuracy throughout that space. And what we saw was that we were able to recover this to greater than indicated and close to a measured resource kind of accuracy within that space. So that's kind of the resolution that we're able to achieve. And that has quite an impact to how you can map a deposit when you get to that accuracy. So going back to kind of trying to map the whole mine, this is an animation I'll show that is a synthetic showing what it might be like to, this is actually to map about a third of the deposit in three sets of detector deployments or arrays that could be kind of stepped through. And I've got density isosurfaces here of, I think it's, they go between about 3 to 4 grams per cc. So nested semi-transparent isosurfaces. And then I'll show what the kind of inversion simulated inversion could be for this area. And I'll just kind of step through the space here. And you can kind of see how it correlates, and we're taking it step by step, but we're trying to see how well we can look at imaging a whole mine or whole deposit. And the idea is that it would be, we're not necessarily exploring to find the deposit, but we want to, as the mining process goes on, more and more drilling needs to be done infilled in order to work up the economics of a deposit, and this can accelerate that process, essentially, hopefully do it with less drilling. And a few years ago, Laura Tyler, the then CTO of BHP, was talking about new technology to make the top 400 meters of the Earth transparent for exploration, and we're seeing how we can do that down to 1 kilometer with these methods. So I will switch gears here and talk about Creighton Mine. This is an example from Vale Base Metals in Sudbury. So it's a massive sulfide nickel deposit in Sudbury, but this is actually primarily a geotechnical problem that we were working on. The objective is to map the base of a rubble zone. So it's an old pit that has been partially infilled with rubble. And the first objective is to map that base of the rubble zone. So they wanted to know where that was, because they're kind of mining underneath and looking at where the geotechnical stability is. And then also there's always the secondary purpose of mapping mineralization that was missed during mining that has happened in the 50s, 60s, and 70s. So any remnant mineralization. And we approach this with an array of 4 holes around the central targets. There's a lot of mine workings here. There's one of the nice things about this method is that it's insensitive to any noise around a mine. So we can put it anywhere in a mine, and there's no noise or interaction with that. So we had 4 drill holes and 4 detectors in each drill hole. You can see the fields of views that come off each detector. And we're looking for an imaging the central part of this in between these drill holes. The first way we approached the modeling was actually with a geometric inversion similar to VPMG, where we were simultaneously inverting for the elevation of this base of the rubble zone and the density of the rubble zone and the density of the host rock at the same time. There's enough information in the data, it's unlike a potential field, that we can actually recover all of those pieces of information at the same time, and they converge quite nicely. We tested it and we kept getting a very robust result. So that's the first part, is to recover that surface, and then the density of the rubble zone and the density of the background or the host here. And then after that, we introduced heterogeneity within each part, heterogeneity within the rubble zone, and also heterogeneity within the basement here. And we got a number of interesting things come out. This was done blind. We did map a sub-level cave here, and also we mapped a pillar here, which is expected to be remnant mineralization. And we went back to Vale, and they told us a little bit about the history of the mining that was going on here in the 60s and 70s. So I'll come up with another image here, this is a section through here. So this is a waste dump. We were talking about kind of things that can impact the data. We actually recovered the density of the waste dump in this inversion. And so, yes, if we could account for it and it would help things below it, but we're also, it's a good validation of the results here. We've got this rubble zone here, and then we've got this sublevel cave that actually caved into the rubble zone above it. And also there was subsidence going on coming back from the pit as well. So we were able to, this is the footprint of the workings where all the sublevel mining was going on in the 60s. And then essentially they were unable to carry on. And so there's potentially a pillar of unmined ore in the middle here. The interesting thing is you can't drill through rubble to test things and what's down there. So this is kind of one of the only ways where you can actually image through an image into these features. And yeah, I think we also did some constrained inversions because this is right along the Sudbury igneous contact of the norite and the granite as well. So that was quite a nice result, and being able to show all of those features from one survey. And I'm going to switch to our
Yeah. So Peter Walker asked if you I'll read it. Have you incorporated gravity or gravity gradiometry to constrain the inversion?
Not this one. Yes, in for other results, yeah, it's very straightforward to do. We do see that the muon, because of the resolution that we get, it kind of drives the inversion when we combine it. But yes, we can do a joint inversion with the gradiometry or the gravity. Yeah.
Hi, I had a question.
Yeah.
For Olympic Dam, but it applies to this as well, you were at 800 meters. So what was your integration time like to get the data you were looking for?
At Olympic Dam, it was on the order of 7 to 8 months. And at Creighton here, it was 6 months. But it really depends on the resolution that you require. It doesn't have to be that long if your target is larger. Or if you're looking you want higher resolution, you just wait and get more muons, essentially.
Right.
So it's a function of what the objective is.
And I had a secondary question for Olympic Dam. Right, you were using array type detectors, right, spread throughout the shafts of the mine. For that, are you looking for or spread out to maximal area, or are you fixing it in on a certain area that the arrays are spread out across?
Yeah, we do a lot of survey design, so we make sure that what the objective is, the volume that we need to image to a certain degree of resolution, that we capture that, and we do need to design the lateral extents and that to get those crossing rays. So yeah, it also is a function of accessibility as well. So logistics comes into it. But yeah, you often do want a good lateral footprint to get good resolution. I will go back to that question a little bit about the kind of the exposure time. In order to get the other way to go about reducing that is just to put more detectors down. It's quite a simple relationship, and actually it's even better because you might have more points of view as well. So you kind of put more detectors down, you can see things of higher resolution or faster. And in the example of the block cave imaging that I'll show at the end, we are getting an image every 30 days. Because that's the kind of the cadence that we want to be able to provide an update on how the cave is developing. Yep. Cool. I'll move over to this was a synthetic study we did for iron ore resource characterization, and the idea is to again see how we can reduce drilling. And we are comparing densely drilled creek models to sparsely drilled drilling with borehole muon detectors in there. And our workflow is something like this. We've got our true density model that could come from very dense drilling. We have synthetic muon data. We add noise to it, and we use that data to generate inversions. We also take the density information that was in those simulated drill holes where the detectors are, and we can essentially do some co-located co-kriging so that's using our unconstrained and our drilling information to do some co-located co-kriging, use that to inform our constrained inversion. I'll go into that in a little bit more detail in a subsequent slide. And when we do this, because this is synthetic, if we have different noise realizations, we can come up with an ensemble of models from which we can get statistics. And the important statistics that we get here is really kind of an accuracy or a bias, like how far we deviate from the true model, and also a standard deviation as well. And if we do that for different array configurations or different survey designs, different drill hole spacing, then we can look at how that compares. And the idea is to get both good resolution or good precision and also good accuracy over the whole volume of interest. So with this study, this is the block model that was provided. This is from 50-meter drilling. And when you're mining an area, it starts off to be quite sparsely filled. And then over the years, where it might be planned years in advance, there's infill drilling that goes on, maybe first to 100 meters, then to 50, and as the years go on. And what we're trying to do here is see, can we get the information at the sparse drilling stage well in advance of when they have to drill it out extensively to define the resource. Not only that, before mining happens, there's a lot of permitting that goes on and environmental impact assessments and things like that. And during that time, that could last a year, no drilling is allowed. So if you're spending that time learning more and more about your deposit without any more drilling, that really advances and accelerates the mining process. You can see on here, this is a density map through the area of interest. There's this low density feature here. This is a diorite dike, and that really impacts the mine plan. They have to mine around it, and they have to plan for that. So they have to really know where that is well in advance for the mine planning. So that's one of the important features that we want to recover, as well as the density informing the grade. So we performed some synthetic surveys with different strategies with 200 and 400 meters that I'll show here. We did others as well. And so this kind of shows you where our synthetic drilling would be. And we would have a few borehole detectors in each hole to map this area. And what we're doing, we're really testing kind of what is done usually, which is 153 drill holes in this area versus 15 in black versus 6 in the magenta here, just to see how well each performs. And the workflow, if I go into kind of how we combine the geostatistics in here, we've got our true density model that we perform the forward model on the synthetic survey. We've then get our data. This is our radiographs, our Z scores again, but in a polar coordinate system. And then we would get an unconstrained inversion, and we can use information from that through domaining and looking at the trends in that to inform the parameters of the kriging. And that, as well as the information that is coming from the drill holes, allows us to do co-located co-kriging. So that's where we have an estimate of the density that is an auxiliary field to guide the kriging as well. So we're providing a lot of parameters to the kriging methodology, and then we can use that to constrain the final inversion. So it's a multi-step process. We're looking at kind of more integrated methodologies, and this is all quite vanilla. Really, it's doing quite basic things, basic inversions, nothing fancy, and quite basic statistics at this stage. So this is the result for 400-meter drilling. On the right is our kind of our true, what we're calling our truth, what we're comparing to. And the top left is what we would get if there were 400-meter space drilling just from kriging alone. So essentially, on this section, we would just have 2 holes, and this is how you might interpolate it. And from those same 2 holes, this is what we can recover from the Muon result. And you can see there are some features in here, this low density here that we've picked up. I think there's some areas on the left that are better correlated. Maybe we're not capturing the density value quite as well. But in general, I think, 50-meter spacing versus 400-meter, there's a reasonable comparison. Definitely better than just kriging alone. And then as we move to 200-meter drilling, if we can look at the kriging alone, I think there's quite a lot that's been missed. Again, this is probably in the wrong place. This isn't imaged at all, or isn't interpolated at all. And I think we're capturing quite a lot of information when we include all the Muon information, all the Muon data as well. So there's a lot that gets improved when we include the Muon data. And if we look at that in plan view, this would be from kriging alone, and this would be from when we've included the Muon data. So we've now started to image that diorite, which is really important for mine planning. There's a lot of other features that are kind of coming in here in general that I think are just an improvement. And so lots that would just be missed at this stage. This could be years before it's mined, but now we're providing a lot more information ahead of time. And when we look at a tonnage reconciliation, so just taking the vertical summation of the density or the mass in the area, we can see that there's a good reconciliation between what's provided from the block model currently, and then what would be done, what we would get from 200-meter drilling. And the difference is in a lot of the area, just a few percent, up to 6% here. So yeah, again, try to accelerate that mining process. I'm just going to go on to any questions on that. Yeah.
So when you're talking about using the results for a constrained inversion, are you using that as like both the starting and a reference model, or what do you mean by constrained?
Yeah. In general, that's what we're doing right now. Yeah, but the other piece of information that you get from kriging is a kriging uncertainty. Okay. So you can actually use that as a weight as well.
Oh.
Yeah. So there's quite a lot that you push into an inversion. Yeah. And essentially you can get a covariance matrix out of it as well, and those covariance lengths are essentially your kind of length scales within the model as well. So there's a lot of synergy and a lot of a lot that can be of information that can be transported from the kriging and geostats world into the inversions. Yeah.
You keep it linear, right? It's a linear problem.
Yes, if you make assumptions.
Do you make it?
Well, I think the kriging makes some basic assumptions about stationarity, essentially, and there's no bias in the data. So there's a lot of normalizations that go into data that then you perform the geostats on. Mm-hmm. So I think that's one of the key things. It's not with every, but that's with that method. There are other methods that you don't need that assumption to be made. Yeah. Okay, so I'll go into our last case study here. This is for the New Afton mine. So this is near Kamloops. I'll just talk a little bit about block caves. Fascinating things. So first of all, it's a mass mining technique. It's a way of extracting a large amount of ore from the earth without digging a pit, without strip mining. So it has the promise of being economical, but there's a lot of capital investment up front. Could be up to $1 billion sunk, not necessarily sunk, but invested into a mine or put into the ground before you start to extract ore. And so that's all the infrastructure that needs to be put in place and to start initiating a cave. And the cave propagates upwards. You're extracting from these levels underground. And as they extract the top of this is called the cave back. So that's one of the features we want to be imaging, is this cave back. And then there's also this muck pile that is forming, which is kind of rubble here. And so we want to also understand what the topography or the topology of this muck pile is. And in between the two is potentially an air gap. So an air gap can form. We don't want it to form, but we need to know if it is forming, because it can be a significant hazard. So what we can do is we can place detectors at the extraction or haulage or ventilation levels at the base of a block cave. And where we have muons passing through the earth, we can then start to get our crossing rays of muons and then start to image the earth. And it's a really nice density contrast, because this is now a rubble zone or a void, so great contrast for us to see. And these can be quite deep, so some of these are initiated 2 kilometers deep. We've done a lot of modeling down to about 1.5 kilometers deep, and we've did I think, I forget the depths that we're at now, but yeah, we're in a couple of block caves now. I'll show you the results from New Afton. But one of the things is it's really important to know how this cave is developing. And the current instrumentation really provides quite good and precise, but very sparse information. So you get point measurements on where the cave back is, and you may only get 1 point measurement a month. So there's a temporal element to this as well. There are trackers that can give you a rough idea of what's happening inside the muck pile, but there's a lot of uncertainty between, a lot of interpolation. And what we are trying to do is go from these point measurements or improve upon, we still include them, to go to a full resolution of the cave back and of the top of the muck pile. And as well as that, provide a resolution or uncertainty around that surface. So going from, yeah, sparse information to a full image of the cave. And it allows us to, yeah, have confidence that the cave is doing the right thing. First of all, we need to make sure that the air gap is not developing. It can be a significant hazard. If there's an air blast, there could be a sudden cave in, and air essentially gets pushed like a piston throughout the mine, and it can be very dangerous. Hundreds of kilometers an hour air blasts get pushed through the mine. The other thing is to understand how the cave is going. You want it to be able to propagate correctly and actually go through your ore body. You don't want it to either stall, and which might freeze out part of your ore body from ever being able to be mined, or to be diluted. So if it's kind of going over to where you've got low grade or kind of host geology, then that can really dilute your ore as well. So that really impacts what you're drawing out at the bottom of the cave. And what's happening at the top of the cave may not be realized until a year later when it gets to the top of the muck pile, bottom of the muck pile, and gets extracted. So really good to know what's going on at the top of the cave. So there's a little animation I'm showing here, and it might, I'll run it a couple of times. What we're showing is the growth of a cave. We've got months going on the top left here. So over 5 years, and I will run it again. And we're showing the cave back surface. I don't know if you can see in gray here, there is kind of our true surface, and the colored surface is what we've recovered. And then we're also mapping the resolution or our uncertainty to that map as well. So we're going on the order of a lot of it's below 15 to 20 Thanks, Dom. 15 to 20 meters resolution, with maybe maxing out at around 25, just at the top in around the 5 years. So I'll run that again, and we're about 800 meters depth here. And so the idea is that we'll recover surface with a resolution over the cave back and the top of the muck pile every 30 days and provide that to the mine.
How much work in the office does it take to deliver that next iterative product, or is it fairly automated?
It's once it's set up, the automation is okay. It always, needs careful monitoring, but it's getting those first few months going is the key. And you also kind of have to make sure you're accounting for background geology, things like that correctly. And
So it's still fairly labor intensive then on monitoring.
yeah, it can be. It's we're always seeing new things in the data, but the main processing flow is quite standard. Yeah. So the idea is to get good resolution around the whole cave back, and provide an accurate and timely result, and look at how that can be tracked along multiple timeframes, the evolution of the cave, and also provide that quantifiable uncertainty. So
What is your density resolution again? It's like 0.1 to 0.2.
Yeah.
So would that be enough to be able to say within the muck pile, like?
Good question. So yeah, that's the thing. Like, it's really hard to see actually within the muck pile. I'll show you an example here. So this is a case study, and I'll talk through this animation. It's from New Gold. We worked with them last year. They're just outside to the southwest of Kamloops, and we'll look at kind of the mine site. There's a pit, which the cave that we are looking at is under the pit, and there's their tailings dam here. So this is the ore body that they're trying to mine, and they're mining this in multiple stages. But they really need to make sure that the cave is propagating through the ore body and capturing the most value for them after a lot of investment. So this is the infrastructure that they've put in place, several levels. We are looking at the second one, but this is their first cave that has already propagated to surface. So there's a bit of subsidence going on, and it's basically underneath the pit. And that's cave A. Cave B is what we're interested in, and particularly the confluence of where cave B and cave A meet. There is mass flowing now between the caves, and they're extracting from where cave B, the extraction level of cave B. They've just initiated cave C last year, and that will eventually go up into cave C. So there'll be kind of mass flowing all the way through at some point in the future. So it's pretty kind of large scale work. These are the locations of our detectors we put around the block cave in the mine working. So close to the extraction level, just kind of out of the way of all the day-to-day workings. And I'll just wait a second, and we'll look at the kind of the detectors that we've got there. We did have three types of detectors in here. And we've got our old gallery detector. We've now retired. We had several of those. Got our borehole detectors we placed in mine as well. And then we've got our panel detector, which is actually for purpose, and we were testing that here. And one of these is the equivalent to about 5 of our borehole detectors. And our array around here was really focused on imaging that confluence of cave A and B, and these are our fields of views. So even though it was designed to really resolve the cave well in this area, we're also getting a bit of visibility into the surrounding rock as well. Let's see, and then we'll zoom in a second, and we'll look at the data. So actually, this is synthetic data from a predicted cave shape they have. So they don't have they don't have a lot of measurements, and but they do have a prediction of where they think the cave is right now. So we use that with the background geology model to provide a synthetic prediction of what the data should look like, and we use that for all of our feasibility and placement of detectors and things like that. And then this is the data that we actually got from the field. So this is what we recovered at that detector. Again, we're looking at a Z-score. So these are in standard deviations. And the scale is 4 to -4. So we're getting very high confidence in these features in the data. And this is our unconstrained, a section through of the unconstrained inversion after 1.5 months. So we are imaging the cave quite well. There's a low density feature. This was an interesting feature we weren't quite sure about at the beginning, and then we're also seeing some kind of heterogeneity on the left here as well. But in general, the idea was to, is the top of this cave? Where is the top of this cave? And we were able to. In this case, this is the voxel inversion result. We can see that, but we also have a geometry inversion result. This is showing the predicted data from the inversion model, the unconstrained inversion model. So we always want to do that comparison. And it's not one-to-one, but we're also combining information from other detectors as well. So there is some stochastic noise. And this is our constrained result. So we actually constrained it with overburden, but also pit fill. So they were slowly filling in the pit with tailings. So we had that as a constraint and the overburden. And then when we did that, we were able to see the this cave shape quite well, but also some features within the cave, within the muck pile as well. And there was an interpreted pillar. So the different parts of cave A were imaged, were mined at two different times, and there's actually a pillar that was put between there for safety and just to keep things from falling down, essentially. And this is another section showing their predicted cave bases versus what we were able to recover here. So it gave them good confidence that the cave was actually doing what they expected it to be doing. Now, what's interesting is that it's okay, if it's behaving as they expected it to, but it's really providing that visibility if it is going off course. There was a few units they were very interested to make sure it wasn't going over into some kind of poorly consolidated volcanic units that they were worried the cave was going to go off course. And also when it would be important to look at these caves at a critical juncture. So when cave C that is being initiated now, when that eventually comes up to meet cave B, you need to know when to stop mining, when to stop extracting in cave B before the cave comes up below you. So those are the kind of timelines when you really need that visibility on these caves that otherwise is really hard to image. So yeah, I think I'll stop there. So hopefully I'll give you a good kind of overview of what we've been up to. I'll give a quick shameless plug before I stop for questions. But yeah, our CTO Doug Shooten is going to be talking at the PDAC and give some actually even more up-to-date results. So not this work, but new results at the PDAC. Yeah, thank you very much.
Few questions already.
Yeah.
People online. Marco, would you like to unmute yourself and ask yourself the question regarding density?
Hey, yeah, sure, done. Thanks. Thanks for the talk. Yeah, no, my question is more like if the data that you got from the boreholes, the density data in the iron case, it came from the Archimedes method or the gamma borehole survey. And
yeah,
if you ever made this comparison, like if it makes any difference to use
that was, we extracted it directly from their kind of highest resolution block model, and but it did actually come from gamma.
Oh, okay,
and that's what was informed. That is what informed the block model. Yeah.
Okay, thank you.
Peter, would you like to go next? Peter Walker. I'll ask the question then. Why would you choose Muon over passive seismic or borehole seismic to monitor the blood caving? Like, would there be an advantage
Yeah, I think it comes down to resolution, really. We've looked at some comparisons actually at New Afton, but yeah, I think being able to actually see that clearly get a real edge or resolution of that cave back, I think that's really key. And you won't be able to get a lot of seismic through the air gap
Very
either.
loose,
Yeah,
yeah.
and really
Or
loose.
head.
Yeah. So there is a also there's a ring kind of above the cave back that is the kind of the seismically active zone as well, and that's quite fractured. So there could be, you might also get quite low velocities through there as well. There, you can image it, and people do use passive seismic, but I think it's not providing the resolution that you can get here.
And then Beth, just one more for online. So Beth Reed asked, can you explain what geometry inversion, what the concept of geometry?
Oh, for sure. Yeah. So that would be basically your parameters that you're inverting for would be a depth or a location, a spatial location, rather than the density parameter or density value. So it's, yeah, moving boundaries around essentially, rather than having a fixed voxel mesh and changing your property values.
On you?
Yes.
I'm always interested in the detector technology. You didn't say anything about it. Is there anything you can actually say about your Muon detectors or how they work, or
Yeah.
trackers?
Well, I guess, what can I say about them? Not a lot, but they all they do is count, but measure the direction.
Oh.
So yeah, often people think that we're measuring the energy of a muon and things like that, and that's not the case.
Okay.
Yeah. Sorry to be so close-lipped, but
That's it.
So there must be a threshold of energy somehow.
yeah, and really we're only interested in the high energy ones anyway. As they slow down, there could be some slight kind of bending, very minor, as they get really down there. But it's really just the high energy muons is what we want. Those are the ones traveling in the straight line. Yeah.
Don't those really high energy ones get really, really rare?
It's a stochastic thing. There's a distribution, there's a population coming down, and that's what we know how many to expect at different depths versus through different density media, essentially. So yes, they're rare, and your counts get fewer and fewer. It drops off exponentially as you go down, but there's enough to get the information we want. And you put more detectors, or just sit there for a year. Yeah. We are, there are ways to generate muons, but not to the energy that you need to look at these depths. Often people ask, can you generate, have a muon gun or anything
That
like
would
that?
be a game changer for you guys.
Yeah.
There's a lot like tabletop Muon, tabletop particle acceleration.
Yeah.
I've got a couple of off-topic oddball questions. Surprise, surprise. Yeah. What's the site here about Ideon going into space, sending muon detectors? You attended, or not you, somebody in your company attended a conference in the NASA, the USGS conference about off-world resource exploration. So are you thinking of sending muon detectors into space around asteroids or something?
I don't want to comment on kind of the direction we're going, but I will comment on something that I find interesting around this. And that's, what I described is how muons are generated like in the upper atmosphere, right? This particle with this chain reaction. And if in different parts of solar system and different moons and planets, you may not have that. But because you may not have an atmosphere. So, but I do understand that on the moon, there's enough enough going on right at the surface that you just get this radiation impinging on the surface, right at the surface, that can cause a chain reaction right there at the surface that can then generate a muon and go to depth. I thought that was interesting.
So this is way future stuff.
On the moon first.
Yeah, we're going to be exploring the other planets. The second one was, and this is really, there was a study done on Oak Island, and it made the TV show. What was the final conclusion out of that? Did you find, you didn't find gold, did you? The treasure,
No,
did you find?
The outcome
caverns?
of it was a void. I think that was kind of an area that was of interest. So I don't know what the follow-up was that of, but there was a
So you
void that
found
was,
something, huh?
yeah, that was imaged. Yeah, and that was an area where we had to account for, because it was so shallow, we had to account for the berms and things right at the surface to kind of get things to work.
This is a few years ago, and I remember Doug telling me that it resulted in a ton of people contacting the company about doing similar sort of treasure hunting in parts of the world.
Yeah. Yeah, there are all kinds of applications. So yeah.
The original application was pyramids, right? Isn't the one that first studied it?
Yeah, and volcanoes as well. There's a lot of work that was done, I think by the Italians and I think Japanese as well, just imaging through the volcanoes. Yeah. Yeah, and the pyramid study certainly put it on the map. Yeah. Very good. Thanks, everyone.
Thank you.
Thanks, Michael.